So far we have been discussing about individual aspects of radiation. So now we are going to, from today's lecture for the next 3 or 4 lectures, we are going to look at radiation exchange between different surfaces. So the radiation exchange would depend on several factors. So the first one is obviously the geometric orientation. Depending upon the orientation of the objects, the radiation exchange is going to be different. Depending upon the orientation. For example, you might have an object which is facing perpendicular to each other, or you might have objects which is facing parallel to each other. So depending upon the orientation between each other, the radiation exchange is going to be different. And it's of course going to be a function of the geometry of the material which is exchanging radiation, and it's going to be a function of the surface properties. For example, emissivity, absorptivity, etc. And it's going to be a function of temperature. So these are the 4 primary factors on which the radiation exchange would depend on. And what we are going to see in the next few lectures, including today's, is that how to characterize radiation exchange between 2 surfaces. And in fact, the net radiation which is received by a surface is essentially what is the net amount after the exchange has taken place between the 2 objects. So there has to be because one object emits radiation, it is absorbed or reflected or transmitted if it is not an opaque object by the other object, and the other object is going to emit, and the reflected radiation is also going to be received by the source object. So there is a constant exchange of radiation between them. So therefore, in order to characterize the radiation exchange, we cannot distinguish between so whatever net radiation that leaves the surface is essentially sum of what is emitted plus what is reflected. So the symbol that we will use is called J, which stands for radiosity. And this is nothing but emission plus reflection. Emission plus reflection is what is called as radiosity, and one could certainly define the spectral, hemispherical, total, etc. All the gory integrals you can define for radiosity as well. Okay, so with this definition, the first aspect we are going to look at in today's lecture is how to characterize orientation geometry. Okay. So we need to define what is called a view factor, or it's also sometimes called as geometric factor. Also called as geometric factor. And so this view factor essentially characterizes the, or it takes into account the orientation and geometry of the 2 surfaces, which is, or n surfaces, which is exchanging radiation. And it is defined as the ratio of radiation or received by, let us say, object J, okay, that is emitted by object I divided by total radiation emitted by object I. So, this is the view factor, okay. So, this term capital F is this symbol that we will use for view factor. So, this defines the view factor as what is the fraction of radiation which is emitted by surface I and is received by surface J, okay. So, supposing I have a point surface, okay, and if the area of this surface is dA1, okay, so that is a differential surface, and let us say I have another surface here, and the differential area is, let us say, dAi and dAj, okay, dAi and dAj, okay. So, if that is the line that connects the midpoint of the differential element and if the distance is r, so the view factor is nothing but whatever is the total emission that comes out of this surface I and what fraction of that is received by surface J. Now, it is the geometry which actually defines what is going to be the fraction. The reason is that not all radiation that comes in all directions of this surface is intercepted by this object. So, it is only a fraction which is intercepted, and therefore, it cannot take all the radiation that comes out of this surface, it can only be a fraction, and that is what is defined as view factor. Alright. So, supposing if this angle is theta I and this angle is theta j, okay, what is the radiation that is emitted by surface I and received by surface j? What is the radiation that is emitted by surface I and received by surface j? How do we find this? So, the first thing is, so this is, so we look, you should remember the definition of the radiation intensity that we discussed at the start of radiation, right. So, that is the, supposing if I is the intensity of radiation that comes out of this surface, okay, and that is I comma emission plus reflection, right. So, note that when we have to deal with radiation exchange, we need to look at both reflection plus emission together, right, multiplied by cos theta I, okay. So, if the radiation intensity vector is pointing in the outward perpendicular direction, so I times cos theta will be the intensity in the direction towards the second object, okay, and that multiplied by dAi will give you the rate. Note that this is flux, right, multiplied by dAi will give you the rate at which the radiation is leaving from this surface in the direction in which it is pointing to the second surface, multiplied by the corresponding solid angle. Multiplied by the corresponding solid angle will tell you what is the amount of radiation that is intercepted by this surface. So we need to find the solid angle that is subtended by this surface on that point object, and that solid angle multiplied by the rate at which the radiation is leaving that surface will tell you what is the differential radiation that is emitted by this surface and is received by the second surface. Okay. Alright. What is d omega ji? What's the differential solid angle? What's the definition of solid angle? D. So note that dAj is pointing in the normal direction, dAj into cos theta j, right? So the area which is pointing towards the emitting surface is dAj into cos theta j, right? So the solid angle is dAj cos theta j divided by r square. Okay, so that's the differential radiation that is emitted by surface I and is received by surface j. Okay, so therefore dqj dqij is I plus r cos theta I cos theta j into dAi dAj divided by r square. Okay. Now if you want to find the total radiation, okay, that is received by the second surface and that emitted by the first surface, we simply have to integrate this qij aj, we integrate this differential element over the area of both the surfaces. Okay, is that clear to everyone? Alright. Now, the spectral hemispherical radiosity, okay, right, spectral hemispherical radiosity is given by, so the symbol I use is J. So supposing if the intensity were to be diffuse, okay, so it's a diffuse emitter. If the surface is a diffuse emitter, okay, so when I say emitter here, I mean it is diffuse with respect to both the emission from its surface plus the reflection, okay, emission plus reflection, okay, alright. So J will be, how are J and I related if it is diffuse? It's pi into I epsilon plus R, okay. So from here we can substitute the expression, and so you will get Qij will be, so note that it is diffuse, which means it is not a function of the angular position, and so it will be Ji integral Ai integral Aj multiplied by cos theta I cos theta j dAi dAj divided by pi r square, okay. What's the total emission from the surface I? What's the total emission from surface I? So this is diffuse, J is it's a diffuse emitter, so it will simply be, what will it be? What will be the total emission? It's diffuse, so it's constant in all directions, and so it will be nothing but Ji is the flux of emission plus reflection multiplied by the surface, right. So that will give you the total rate of emission from the surface I. So with this we can now define the view factor as Ji integral Aj cos theta I theta j pi r square dAi dAj divided by Ai Ji. So note that this is valid only when it is a diffuse emitter, otherwise this J will go inside the integral and you will have to integrate over the whole area. So note that if it is diffuse, then the area scales out like this, otherwise you will have to integrate over the whole area, right, because the differential amount of emission plus reflection is not going to be dependent on the position. Okay, so now I can cancel out the Ji's, and so it will be Fij will be 1 by Ai integral Ai Aj cos theta I divided by pi r square dAj. So this is the general formula for view factor if the emitting surface is diffuse. It's very important. This is valid only when the surface is a diffuse emitter. Diffuse emitter is where the emission is now independent of the angular position. What will be Fji? What will be Fji? So that's the view factor for emission which is leaving surface 2. Maybe I'll put the cartoon here. So here is surface J and here is surface I. Okay. So Fij tells you what is the view factor for emission which is coming out of surface I and is received by surface J. Fji is emission coming out of surface J and that fraction which is received by surface I, right. So what will that be based on this expression? It will be 1 by Aj integral Ai Aj cos theta I cos theta j pi r square dAi dAg. Once again, this assume that it's a diffuse emitter. Okay. So from this you can clearly see that Ai Fij will be equal to Aj Fji. Okay. Because it's this geometry which is seeing the other geometry, and this is essentially the relationship between the solid angles. What you have essentially connected is the solid angle which is subtended by this object on J and solid angle which is subtended by J on I. So we have just taken care of that, and this relationship is what is called as reciprocity relationship. So it's very important to find these relationships. We are going to find a couple of other relationships in a short while. So the first exercise, whenever you get a radiation problem to be solved, the first exercise is to find the view factors. That's the first step when you want to calculate radiation exchange between any surface. So such conservation relationship helps you in finding various view factors with almost no effort. For example, if you know one view factor, the other one comes for free. So as long as you know the areas, you should be able to find the other view factor. So such kind of conservation relationship helps you in finding as many view factors as possible without doing the gory algebra. So if you know this, you don't have to integrate the expression again. Okay. Alright, supposing I have n surfaces, supposing I have n surfaces in an enclosure and it is exchanging radiation. Okay, so we have, let's say they are maintained at T1, T2, etc. up to Tn. There are n surfaces and each of these have a surface area of A1, A2, AI and An in general. Okay. So now from here we can easily read, supposing if I want to calculate F11, okay. What is F11? So supposing if it is a planar surface, what is F11? So whatever emission which is actually coming out of this surface, which is planar, okay. So I said it's a planar surface. So whatever emission that comes out of this planar surface is not going to be intercepted by itself because of the orientation, right. So F11 is actually 0, or in general one could say that convex surfaces, for all convex surfaces, the view factor of itself is 0. So if I is the tag that I give to the surface, then the view factor to itself is 0, and if it's a concave surface, Fii is not equal to 0. Okay. So that's an important observation. What about F sum of F11, F13, 1n? What will be the sum of all the view factors? Will be 1, right? Because by definition, view factor is the fraction of radiation that is emitted by that surface, by a surface, and as received by another surface, right? So this should be equal to 1, because if it is a closed enclosure, note that this is valid only for a closed enclosure. If it is not a closed enclosure, then you will have to identify or intuit as to what should be the correct view factor summation that you have to use. Okay. We will see some example problems where you will get a much more clear picture as to what you should do when you have a open enclosure. Alright, so it's essentially F1i, I going from 1 to n, that's equal to 1. So this rule is valid for all the surfaces, right? So in general, I can write this as Fki for all k going from 1 to n. Okay. So this rule is called a summation rule. This is called the summation rule. So if you know n minus 1 view factors, the nth one comes for free, simply by using this summation rule.